Hello, myself Pratyush Moria. I'm going for a topic reinforcement learning and robotics. Um, the case study topic is how to train your robot with deep enforcement learning. So we will present a case study of application of deep reinforcement learning to various robotics tasks that we have studied. The applications span manipulation, grasping, test location. The sensory input used range from low dimension to propagative state information to high dimension, and the action space include both continuous and discrete actions. So learning manipulation skill. Reinforcement learning of individual robotic skill has a long history. That is, reinforcement learning provides some scaling capabilities in this regard. Uh, Deep neural network policies can alleviate the need of manually policy. A class provides a moderate amount of generalization to variable initial conditions, and perhaps most importantly, allow for end-to-end joint training for both perception and control, learning to directly map high dimension sensory input such as image to control output, and end-to-end training itself present a number of challenges. So for guided policy search, there are first reinforcement method that could be practically applied to learn individual network skill for image-based manipulation task. The basic principle behind this method is that network policy is guided by another reinforcement method, typically a model-based reinforcement algorithm. Uh, the neural network policy is referred as global policy and is trained to perform the task successfully from the most necessary observation and under moderate variability in the initial condition. For example, the global might be required to put the red shape into the shape sorting cube at different position. This requires the policy to implicitly determine the position uh, of the whole. However, this is not supervised directly, but instead the perception mechanism is learned end to end together with control, and supervisor is pointed from multiple user based learner that learn separate local policies. This is the image that we have seen that for to place red trapezoid block into a safe sorting queue. It learns local policies for initial position of the queue, which can be raised automatically using the robot left arm. And the important point of is that set of assumptions underlying the guided policy search method. Typically, such method assume that the local policies can be optimized with simple uh, reinforcement method like LQR, uh, PI2. The reasonable for robotic manipulation task trained in the laboratory setting, but can be a difficult open worldwide environment where the low level of systems cannot be effectively measured, whereas resetting the environment poses challenge. Uh, None for learning individual robotic skills, guided policy search method have been applied widely, end-to-end range of behavior from inserting object into containers and putting caps on bottles, opening doors, and shooting hockey uh, pucks. Guided policy search methods are very effective in terms of number of samples, particularly as compared to model-free reinforcement learning algorithm. The model-based learning policy can be acquired the local source quickly and effectively. For model-free skill learner, uh, limitations of there is some limitations such as to the need to decompose task into multiple distinct and repeatedly initial state, or the end of model-based optimizer that typically operate on a low dimension state representation, but the of a uh, cost of sustainable increase in the area of number of samples. Uh, Over little of 2 hour interaction, the comparable Lego block stacking experiment report by year required about 10 minutes of training. Although there is a long history of model free reinforcement in robotics, um, the RL algorithm has been used more recently for tasks such as door opening and assembly and stack of object with low dimension state observation. These are the methods. Uh, we have generally found manipulation tasks such as stacking Lego either with single position or with some variation in positions. Here is the two image for block stacking and door opening. Here is the model free based algorithm learning skill with low dimension state observation. First one is the learning to stack Lego block, and second is learning door opening. With the deep reinforcement learning algorithm, we have been applied a lean manipulation skill directly from real world data. Have used a policy algorithm based on Q learning. Uh, on policy gradient algorithm, then a standard configuration of this method can require around 10 times the number of samples. Um, Policy methods such as TRPO. In some cases, this increased sampling requirement may be justified by use of better stability and better robustness to optimal hyperparameter settings. The model-free reinforcement algorithm would excel at learning directly from raw image observation. In practice, that is particularly difficult training regime and good real-world result with model-free reinforcement learning directly from observation, certainly with improvement in the efficiency and stability. For learning predictive model for multiple skill with visual foresight, there are situations where in a single skill in all the robots will need to perform sufficient robots where learning each skill from scratch is incomplete. So in that case, there is a great deal of knowledge that can be shared across the task to speed up learning. We have a study of scalable multitask learning of vision-based manipulation skill with a focus on tasks that require pushing or picking and placing objects. Uh, our goal to learn many tasks with many objects, and more practical to learn from data that can be collected at a scale without human supervision or even a human attending the robot. It becomes imperative to remove assumptions such as regular effects of the environment. For learning to grasp with uh, reinforcement, their most significant open problem in robotics requiring complex interaction with previously seen object, a closed loop, vision-based control to react for dynamic situations. For most object interaction behavior require wrapping the object as first step to allow the visual problem to completely separate from the control problem, which become an open loop for control problem. This separation signifies the problem. The drawback is that approach cannot be adopted to dynamic movement or its strategy while executing the grasp. There are a number of studies have been done for closed loop grasping in contrast to this method, which frame closed loop grasping as a solving problem. There is a general purpose uh, reinforcement algorithm to solve the grasping task. which enable multi-step reasoning. In other words, the policy can be optimized across the entire trajectory. Because of the policies learned by the optimizing the reward across the entire trajectory, um, and is constantly replanning the next move with vision as input. The policy can be learned complex behavior in a self-supervised manner that have been hard to program, such as simulation, pre-grasp manipulation, dealing with cluster scenes, and retrieval behavior can be learned because the policy can quickly react to the visual input at every step, which may be shown in one step that object drop after the gripping lifted it from the beam, and thus it re-attempted to grasp in the knee location, the object failed. Um, the, the leaning less locomotion, although walking and running seems effortless activity for us, designing locomotion controller for less robot, which is long-standing challenge. The RL hold the promise to automatically design high-performance locomotion control. In this case study, we will apply reinforcement technique on the miniature robot, a mechanically simple and low-cost platform. There are significant challenges and develop various learning-based approach with which agile and stable locomotion emerge automatically. Um, there is a prototype tool for robotics which can help to bypass many changes of learning on real systems such as data efficiency and safety. For general purpose algorithm and simple reward for working fast and efficient, we can train the robot to work in within 2 or 3 hours. The policy learned simulation is usually does not work well on the real robot. With this real-time transfer technique, we can successfully deploy the controller learned in simulation on the robot with zero and a handful of real-world experiment. Uh, it is important that robot can continue their learning process in the real world in a real life fashion to adopt the policies uh, to the changing and dynamic uh, condition. There are main challenge for real world of location skill. The first sample efficiency and need about 10 millions of data samples that further which can take month of data for collection on the robot. Say robot safety is another real world training with the exploration stage of learning. The robot often noisy equitation pattern that cause jerky motions and wear and tear of motors. For uh, the last challenge is asynchronous control on a physical uh, robot sensor measurement, neural network inference and action execution usually happen simultaneously and asynchronously. These observations that the agent receive may not that be computation to a communication delay that asynchronous break the fundamental assumption of the MDB process. For scripted policies, uh, for betterment for demonstration, we can come over the exploration challenge with moderate amount of engineering and scripted policies that can serve as initialization. Scripted policies can be incorporated into the learning process in such a way that demonstration can provide considerable benefit. Although there are aggregations such as data for a small number of demonstration would have limited effectiveness, the advantage of scripted step policies can be used to collect very large data set. In the final QT option experiment, the scripted policy was used to collect 2 lakhs of attempt with success rate of 30%. Although success rate is lower than final policy, and with success of 96% of the time, it was sufficient to boost the effectiveness of vision-based crash in skill. Here, there is two images. For first image, there are close-up of the robot grasping setup, about 1,000 usually physical diverging training object. Each robot consists of arm with two-finger gripper, and over the shoulder, there is a RGB camera. For a second image, there is 8 graphs from Q2 option policy. There is some strategy discovered by our method. There are 8 rows of marked as ABCD here. GH. For AB, there is pre-grasp manipulation. For CD, there is adjustment. And for EF, there is dynamic object and recovery from the perturbation. And EG is the clutter. That's all for about scripted policies. There is another reason we can pre-calculate the reply buffer only with scripted policies to help the ratio of successful and unsuccessful short uh, uh, for policy used to generate data. Once it is certain amount of performance, our rule come only to start using the trained policy for data collection once it is more than 20% of success. Thank you.